So this is our final presentation for CSCE 689 reinforcement learning, and our project is called Wall Street Bots by Jason Raether and Chanwei Hu. So the task we're trying to solve is actively trading in the stock market. The stock market is essentially a sequential decision problem. There's plenty of data about stock market share values over time that change that we can use to encode a state space for the agent to learn. Some key factors that affect this decision-making about buying, selling, or holding for the agent is the stock price, portfolio balance, moving average convergence divergence, or MACD, volatility, and public sentiment about the stock. These are all things that reinforcement learning can use to learn the task. Our MVP formulation for the stock trading is as follows. For each stock, there are 4 features: the number of shares held for that stock, the stock's open price at that time, the MACD as mentioned before, and for the sentiment augmented state space, we use a sentiment feature also. And there are 30 total components, and we use the Dow for that. So there are 30 tickers. And so overall, the state space dimension is 121, with the last dimension being the account balance for the agent. Each action is between -1 and 1 in a continuous range. That represents the percentage of 500 shares that the agent either buys or sells. If it's negative, it sells. If it's positive, it buys. And these are all floored and compared with the current state of the agent. So it can't buy more than it can afford, and it can't sell more than it owns. If A is between some small bound, then we do nothing for that ticker. And so since there are 30 tickers, there are 30 actions. The reward is the difference between the updated and previous total asset worth. So the asset worth is calculated by multiplying the shares held by their market price, and we also add the current balance of the agent to that. So for Reddit sentiment, we analyze the subreddit Wall Street Bets, which is from the online forum Reddit. To extract sentiment, we look through the previous 50 top posts at a given day, and we search for relevant tickers from the Dow. If we find the tickers in the text of the posts, then we increase the sentiment score.
Okay, so in order to solve the trading problem, we use 5 well-known algorithms, which are all able to solve problems with continuous actions. Moreover, instead of using the traditional multi-layer perceptron as policy function, we try to apply long short-term memory, which is LSTM for short, to see if it can capture the trend from the historical data. Note that not all the algorithms support LSTM policy. We only use LSTM in A2C and PBO. And this table shows the results with different starting balance. We train our agent from 2009 to 2020 and evaluate the trading performance from January 1st to April 30th. From the result, an interesting observation is that when the amount of starting balance is small, TD3 achieves the highest return. As the amount gets bigger, all the algorithms have a competitive return. So it doesn't matter which algorithm is used for trading. And this table tells that how the sequential length of LSTM affects the performance. The bold text indicates the highest return for hourly and daily trading in each methods. We can see that the agent performs well when the sequence length equals to 32 or 64. This is probably because the agent can obtain sufficient information when the sequence is too short. And it's hard for agent to optimize when the sequence is too long. So this figure presents the overall account balance of all the algorithms from January 1st to April 13th. The upper one is the curve of using daily interval, and the bottom one is uses hourly interval. We can see that with LSTM policy, which is red and blue line, both perform well compared with using MLP policy only, which justifies LSTM did help extract historical trends.
So here we compare the results of the sentiment augmented state space models with their regular models, and we actually observe worse performance with the sentiment augmented state space models. We do have to change the training period between 2016 instead of 2009 because the subreddit doesn't have enough active posts on it really before 2016. And so there's a bunch of explanations for these negative results. The stochasticity of the sentiment could be explained, could be an explanation, and also the fact that the sentiment is a very sparse vector, and it might be impossible for the agent to find a relationship between the score and the increased price. There's also less training data compared to the baseline non-sentiment models. There's also a high volatility event that happened in our testing data, which may have impacted sentiment, and also the naivety of the sentiment score. So just increasing a score because somebody talked about a certain ticker does not necessarily point to whether or not that ticker is good to trade on, because in reality, it could be about a negative sentiment about that ticker. So in conclusion, we attempted to train an agent to solve a stock trading task. We evaluated multiple models like A2C, SAC, along with LSTM and non-LSTM policies. We tried augmenting our state space with sentiment analysis and discovered that this actually hurts our performance. And in future work, we would explore using more sophisticated sentiment analysis techniques for both positive and negative sentiment, as well as fine-tuning models and adding extra other financial statistical features.